I'm Brad Orr, chair of the physics department, and it is a gives me great pleasure to welcome you to the 16th annual Ford Distinguished Lecture. We want to thank the Ford Motor Company for endowing this 16 years ago with a generous donation so we could bring distinguished speakers from around the world. The Ford Motor Company has a long and deep history with the University of Michigan, and its generosity to the physics department is appreciated. Just this morning, I got a notice concerning a meeting that's coming up in early April between the Business Engagement Center and researchers here, and Ford is offering grants to people to help them work on projects, and it's just one small part of the interaction between Ford Motor Company and the University of Michigan, so I thank them very much. This annual lecture is made possible through an endowment in 1999 from the Ford Motor Company. Ford's gifts allows the department to bring, as I said, world-class visitors to interact with students and faculty. So our guest today has spent the whole day, we've kept her busy the whole day meeting with faculty and students, telling us about her work and sharing ours with her, as well as delivering this public lecture. We're very pleased to have with us today representatives from Ford. We have Donna Burkhardt, who is the Vehicle Core Software Manager. I am told that vehicles nowadays are simply a computer with four wheels. That's a reframing of what an automobile is. We have Dr. Andy Drews, the technical expert, advanced X-ray analysis, automotive materials, and team leader, energy storage materials research. Dr. Jim McBride, Senior Technical Leader, Autonomous Vehicles Research and Advanced Engineering. Jim is a U of M physics alum from our department. And we have Mark Johnson, IT Executive Technical Leader, all visiting us from Ford. Could they stand up, please? We also know that there are a number of other Ford representatives here. I can't read them all, but could I have all members of Ford, retired or active, please stand for a round of applause. So I want to thank you for joining us today and extend a most sincere thanks to Ford for making this annual event possible. And now I'll turn over the microphone to Professor Katie Fries, who will introduce our speaker for today. Katie.
Well, I am thrilled to welcome Sue Coppersmith today. So I'll start by telling you about how she got started as an undergrad at MIT, then was for a year a Churchill Scholar at Cambridge, got her PhD at Cornell, doing her thesis at Bell Labs, spent a lot of time at Bell Labs, a postdoc at Brookhaven, followed by a postdoc at Bell Labs, visiting professor at Princeton, followed by staff at Bell Labs, then was a professor at the University of Chicago from 1995 to 2001, at which point she went to the University of Wisconsin in Madison, where she is now the Robert E. Fasnacht and a Vilas Professor of Physics. She's a leading condensed matter theorist who has worked on a broad range of topics and has made substantial contributions to many different areas. I'll just mention a few: self-organized criticality, granular materials, superconductors, and today telling us about silicon quantum computing. She has many honors, including membership in the National Academy of Sciences. She's a fellow of the American Physical Society, a fellow of the AAAS. What does that stand for? American Association for Advancement of Science, I think, right? Yeah, thank you. So the Ford guys knew this, the physicists didn't. That's interesting. She's also a fellow of the American Academy of Arts and Sciences. And as far as service contributions, was chair of the University of Wisconsin Physics Department. She was a member of the Nordita Advisory Board, but not at the same time that I was at Nordita. Chair of the External Advisory Board of the Kavli Institute for Theoretical Physics in Santa Barbara. Chair of the Division of Condensed Matter at the American Physical Society, Chair of the Board of Trustees of the Gordon Research Conference, Trustee at the Aspen Center for Physics, and Chair of the section on physics of the AAAS. So we're very glad that she was able to join us today, where she's going to tell us about From Bits to Qubits, a quantum leap for computers. So Sue, thank you so much for being here.
Okay. Oh, thank you. Great. Hi. So first of all, I want to thank everyone in the department for hosting me, and it's a great honor, and I really I'm humbled, but yet proud to have the opportunity to give this lecture. And I want to thank everybody who talked to me during the day, the students and faculty, and had a really fun and interesting day. And I want to thank you for making the time to hear about quantum computing. So I'm going to talk to you about why quantum computing is a thing nowadays, and then at the end I'll tell you a little bit about the work that I've been doing. So I guess I wanted to get a sense of how many people here have heard about quantum computing. So everyone's heard of it. How many people sort of feel like they know what it's about? So less, good. Okay, so and so for those of you who know about quantum mechanics, I will say hopefully I'm going to introduce quantum mechanics design for people who don't know much about it, and so hopefully you will feel like, oh yeah, I know that. And for those of you who don't know, I just wanted to let you know that that's sort of part of it, is to explain to you why quantum computing is fundamentally different from the computing that you know. Okay, so oops, that was the wrong thing. Okay, so basically I want to motivate quantum computing by talking about classical computing. And I always want to just, I was taught when in school, whatever, that you want to relate things to something people are familiar with. And so I'm going to talk a little bit about what's in your phone. This is an iPhone. But it's just, you could do an Android and it would be the same, okay? And the thing which we may not appreciate is, how much progress there's been in computing in my lifetime. And I'm probably older than most of you, but nonetheless, even in your lifetime, there's been incredible progress in computing. And so here it is. Now, I was born in 1957. So this is a little older than me, but anyway, so the thing is, this is a transistor radio from 1954, and it played, it was a radio, so you know exactly what it did, and it cost $49.95, and which is equivalent to about $450, and it had 4 transistors. And this is a picture of an iPhone 6. Now, I'm cheating a little because it's not the latest iPhone, but nonetheless, an iPhone 6, which you can buy on Amazon for $359.95. And by the way, without a contract, because it's cheating if you include the contract, because the contract is subsidizing the phone, so you have to make it unlocked, is less than the transistor radio for 1954, and I found a really good deal for refurbished, but again, that's cheating. But still, nonetheless, if you're in the market, hurry, it's on sale. Anyway, and so the point is that, for the same money, or actually a little less, instead of getting 4 transistors, you get 2 billion transistors. And that increase in computational power for the same money underlies so much of what your phone is good for. It's, you take movies, you know what you do with your phone. Okay, so, and so there's a law. It's not really a law of physics. It's an observation, which is called Moore's law, which is that the number of transistors in a computer has been growing exponentially since before 1970, but here it is here is like time, so this is 1970, this is 2011, and this is sort of the number of transistors in computers And it's been growing exponentially, and here it is at 2 billion, and 2 billion is the iPhone 6. Okay, I didn't put in presenter notes, but the iPhone 8's right on the curve. I checked it. Okay, so come on. Oh, we'll do that. And okay, so how does this work? Okay, and it turns out that the size of the phone, got it right here, right? Is actually a little smaller than the transistor radio. So it's not like anything got any bigger. It's just that you got more transistors into the same space. And so I looked up the number of transistors. This is the number of transistors in the iPhone 8. Okay, it has 5 million per square millimeter compared to 200 transistors per square millimeter in 1970. So again, what happened was just, everything is sort of the same, except that there's like more and more stuff in the same amount of space. All right, the transistors are made smaller and smaller, and it turns out that that is the fundamental mechanism by which electronics, the power of electronics, has been increasing for the last 50 years. So here's a little graph of the feature size versus time, and actually you can sort of see here that it seemed to get a little faster in 1990, and there's actually an interesting story about why that is, but sort of off the subject of the talk. But if you're interested, I can tell you about it. You can ask me in the questions. Anyway, but the point is, here it is on this graph, and it turns out the iPhone X is at 10 nanometers, which is 0.01 microns, and it was introduced in 2017. So it's like we're right on the graph, okay? And this is the basis of continued improvement in electronics. And these are just pictures of fab facilities, okay? And so this was the previous generation for the iPhone 7, and the latest Android is essentially made with the same chips, but I own an iPhone. Apple doesn't pay me, but I've been doing it with iPhones. Okay, and this one is the iPhone 8 chips, and the X is the same. Okay, and so basically what's happening is that the incredible increase in computational power is just driven by making transistors smaller and smaller, and the way laws are. Laws of physics is like you'd say, well, okay, it's a law of physics, it has to be true, but this Moore's law is what this is called, and this is a law which we know can't be true. At some point, it has to fail, right? And how do we know that? Is just basically, it turns out that atoms are a finite size. And this is a surface of silicon, okay, it's an image of silicon, and with 10 nanometers marked. And you can see, and again, 10 nanometers is where we are now, and you can see there just aren't that many atoms there. And so that like once you get down to one atom, something has to happen, okay? That this idea that we're just gonna shrink things more and more and more is gonna stop working, because you can't make a transistor using today's ideas that's smaller than one atom, all right? And so this we know, and we've known it for a long time because people are capable of drawing graphs. This is a cartoon, but hopefully it reminds you of the graph you saw on the previous slide, that we just continue the line, and if you continue them where they are now, this 1 nanometer is the size of one atom, and those graphs are going to intersect pretty soon, all right? Within the next 15 years, for sure. And so people have been worrying about the question of like, well, okay, the path we've been taking since 1950 for improving electronics is going to run out of gas, and what do we do then? And you can see where, like, once you put it that way, there are many different axes that could be the source of further improvements. But one of the ways is the idea of using the fact that physics on length scales of 1 nanometer, which is the size of atoms, is actually fundamentally different than the physics that we're used to. So the transistors in my iPhone are sort of fundamentally obey they act like things that are similar to what we have in everyday life. They're sort of electrons that we sort of know where they are and things like this. And but when you get down to the scale of single atoms, that's no longer true because the physics is, the fundamental physics governing microscopic objects is quantum mechanics, and quantum mechanics is fundamentally different than than the physics that we're used to on large scales. So what I'm going to do now is try to give you a sense of like part of what makes quantum mechanics so strange if you're used to living in the everyday world in which we live. Then I'm going to sort of say why in the early 80s, Richard Feynman, who was a very famous physicist, came up with the idea of maybe you can use the properties of quantum mechanics to make machines that were more powerful computationally than the computers that we have now. Okay, so that's what's coming next. Okay, so what I'm going to do now is to try to give you some sense of how strange physics is once you're on the scale of single atoms. All right, so I'm going to do it by talking about spins. And in the end, when we talk about the quantum computer, I'll show you like a couple of qubits, things like this. And you can think of the qubit as acting just like a spin. So like, you're not going to waste any brain power thinking about spins in terms of this talk. Okay, so if you think about spin, it's like, you have a top, it's rotating around, and there's a vector that describes the axis about which the thing is rotating, okay? So that's what this is supposed to be a picture of. And classical mechanics is like what we're used to in the world. So if you had a gyroscope or just anything that's rotating, or the Earth on its axis, anything like that, you would say, well, okay, there is, you can describe the spin by, how fast it's rotating around, and that we think of as being a spin magnitude. But then there's also the direction that the spin is pointing, all right? And so classically, the spin can point in any direction. So I have my finger, and I'm rotating it around, and, it can point anywhere. But in quantum mechanics, which is what governs physics at the smallest scales, it turns out that the spin doesn't really point at all. Well, okay, if you measure the spin, you only get certain values for the component of a spin in a certain direction. So you'd say, okay, let's suppose we know the magnitude of our spin, and it could be pointing this way, and then the magnitude in this direction is, is however big it is. And then if I rotate the spin a little bit, that magnitude in that direction just goes down by a little bit. But in quantum mechanics, if I measure the the component of a spin in a certain direction, I get either this value or another value there's a gap, okay? And there are only finite number of different values you can get for that measurement. So classically, you can get anything in a continuum, but quantum mechanically, you only have a finite number of results you can get. And so that's how we say that the spin is quantized. And you get one value or another value that's a finite distance away, okay? And so what happens in quantum mechanics is that you only get one of a finite number of values. And in the cases that I'm going to tell you about today, you actually have only one of two values, and you say, oh, either the spin is up or the spin is down. And then the lingo is the spin is h bar over 2 or minus h bar over 2. And h bar is just the number that tells you that if you have a spin that is either up or down, how big the quantum is that describes the difference. Okay, so what happens is that if you take a bunch of spins, all right, so here we have a bunch of spins. Now we're going to be talking about quantum mechanics. You have a bunch of spins, and what you can do is experimentally, you can take all the spins and line them all up, and then if you measured this component, and the spins are all pointing this way, every time you measure spin, you get h bar over 2. You get the same value, all right? But if you take the same spins and prepare them so they're pointing this way, again, classically, you might think, oh, all right, well, I'm pointing this way, so if I measure the vertical component of things that are pointing this way, the vertical component will just be 0. But that's not what you see. What you see is when you measure the vertical component, half of them are positive and half of them are negative. Okay, so every time you measure the spin, okay, it turns out you always get either h bar over 2 or minus h bar over 2, but if you think the spins are pointing this way, half of them are up and half of them are down. Okay, so classically you would measure that component and get 0, and quantum mechanically you always get a finite number. Okay, so it's really fundamentally different. And this was actually one of the key experiments in sort of the origin of quantum mechanics, which was basically a century ago. And it was one of the really shocking things was that you always measured a component of the spin no matter what direction you looked, no matter how you prepared them. So that's odd, and I wanted to tell you about it. But then the other thing which is odd, and which makes it a real challenge when you're trying to think about making a computer that obeys the laws of quantum mechanics, is that whenever you prepare a system, when you try to measure it, you always screw it up. Right? And so this is called the measurement. So it's called here that if you measure a system, essentially always, when you measure, you change the quantum state. Okay? So here you have the thing I had before, where I have my well, what I did here is I said, oh, okay, I'm going to have spins that look like this. And then I measure them, and I'm along this axis. And if I do that, half the time, I get this way, and half the time I get that way. And I can't predict ahead of time which one I'm going to get. And that, again, is another really strange thing about quantum mechanics. But I do know that after I measured it the first time, after that, I get the same answer every time after that. Okay? So in other words, I start in a situation where, half the time I get up and half the time I get down. Okay? And so here I have 4 electrons, and half of the time I got plus h bar, and half the time I got minus h bar over 2. But then once I've measured it, after that, I always get the same answer again. So here, I measured it, I got plus h bar over 2, but then after I measure it, I get the same answer every time afterwards. Okay? So and meanwhile, if I look at this population, again, I can completely not predict, but if I know I had it before, then I always get the same answer again. So the measurement is completely changing what happens afterwards. Okay? And so that's called the collapse of the quantum state. Because again, you started in a situation where half the time you would be up and half the time you'd be down, but after you measure it, then it just picks one and stays that way forever. So those are really strange. Really strange laws, and it's sort of everything seems indeterminate. Like I set up these spins, and half the times they do one thing, and half the time they do another, and I can't predict which one, and then when I measure it, it makes it all different. And so, and everything I told you was known in the 1920s. But what is new is the thought, and the more than the thought, the evidence that even though quantum mechanics is strange, there is a possibility that quantum mechanics will lead to greatly enhanced ability to do some sorts of computations. Okay, so that's what I want to tell you about now, is why, even though quantum mechanics is this strange, it still might be computationally useful. Okay, so this argument that I'm going to tell you now was, again, originally put forward by Feynman, and he was the first one to really sort of say, let's think about quantum mechanics not as terms of what we don't know. I've been telling you about, you prepare the spins and you measure and you don't know whether they're going to get up or down. But he said, let's think about in terms of the information you need to specify a quantum state and how much information is in there. And what he showed was, pointed out, was the amount of information is much, much larger than in a classical system. So now we're going to be flipping from, in the classical system, we know exactly the direction the spins are pointing, and in the quantum system, we just measure these things that sometimes are up and sometimes are down. But he pointed out that despite that, the quantum system has much, much more information in it. So that's what I'm going to tell you about now. Okay, so we're going to do this by doing brand X, and again, brand X are spins or vectors that we know about, the vectors we have intuition about. And so here's a spin. And what I'm going to be doing again is mostly I'm going to be thinking about spins whose magnitude is fixed. So if you want to describe the state of the system, you just need the direction that the arrow is pointing. And there, if you're used to Euler angles, I drew them. So basically I say, oh, it's a certain amount. Well, okay, the latitude and longitude of that vector. Okay, so here this thing theta is the latitude, right? Like 60 degrees north, but then the longitude tells you where you are east and west, okay? And that's this angle phi. So there are two numbers that describe that spin. And they're real numbers, and you can precisely say what they are, but there's still only two numbers, okay? The other way of saying it is that, I have three components. I have the x component, the y component, and the z component, but I fixed the length, and so I have two left over. Okay, so there are two ways of understanding why there are two numbers. So quantum mechanically, what happens here is you actually have, again, two numbers, okay? But it turns out that the values of these numbers are quantized. What I mean by that, again, is that there are two things, one of which is the magnitude, which we fixed, and then the other one is like the value of one of the components, which you can specify, all right? And that number is only like either, h bar over 2 or minus h bar over 2, so it looks like you've lost a lot of information right there. Okay, but it turns out there are two numbers, and when those two numbers for this fixed amount, for this fixed spin magnitude, those two numbers that describe whether you're up or down are actually the qubit states. When we turn this thing into qubits, this qubit states are just whether the spin, that component's up or that component's down. Okay, but at this point you're like, well, we haven't gained anything. But what Feynman pointed out was the following. Is that if you have a bunch of spins, or a bunch of qubits, okay, and they're classical spins, and you want to specify the state of those spins, well, what you do is you say, well, what's the direction of the first spin? And you've got theta 1 and phi 1, the latitude and longitude of the first guy. And then you have the latitude and longitude of the second guy, and the latitude and longitude of the third guy. And so for every spin, you have two numbers. And if you take two numbers for every spin, you can completely specify that state. So that's why I said that if you have a classical set of spins, you can specify the whole thing using 2 times the number of spins. And if you have 2 n numbers, that's how many numbers you need. But quantum mechanically, what happens is that I've got, the first spin can be either up or down, and there's some, there's a state there, and there's an amplitude of that first spin being up. Second one can be either up or down. Third one can be either up or down, and you can get all combinations. And so here is, again, I called up 0 and down 1. And so here's up, 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 and down, up, up, down. And there are sort of two possibilities for the first spin, 2 possibilities for the second spin, and 2 possibilities for the third spin. And so you get all combinations. So here you have a number that describes the amplitude of this configuration, 0, 0, 0, a number for the amplitude of 0, 0, 1, and a number for all of these amplitudes, and there are 2 to the n numbers. So when you have 3 spins, you have 8 numbers, okay? So for one spin, I have 2 numbers. For 2 spins in both cases, I have 4 numbers. But then when I have 3 spins, I have 8 numbers for the quantum case. And when I have 4 spins, I again double the number of numbers. And so classically, the number of numbers I need to specify the state is growing proportional to the number of spins. And quantum mechanically, the number of numbers I need to describe the state is growing exponentially with the number of spins. And so if I have even 10 spins, 2 to the 10 is 1,000, and 2 to the 20 is 1,000,000. And so not very many spins, I have like lots and lots of information in the state to describe the quantum mechanical state. So that is the fundamental reason why a quantum state has much more information than a classical state, because the amount of information you need to describe that state is growing exponentially with the number of spins in there, okay, versus linearly. So it's a huge difference. Okay, and so Feynman had the original idea of saying, well, look, I mean, if you have a quantum system, there's much, much more information in there, and maybe we can use that to do computation. And, okay, he sort of published this idea in 1982, and it was Feynman, and he was already famous, so he could publish just ideas. But the thing was, it was completely unobvious that this was actually a viable way to do computation because of what I told you before. Remember I said, oh, okay, when you measure, you screw up the wave function. You, quote, collapse the wave function. So it's true all that information's in that wave function, but then you do a measurement and you lose most of the information. And so it's not at all obvious that you can take that information that's in a quantum mechanical wave function and actually use it to do computation. And so, so this was this is where it stood in the 80s, and sort of the whole field of quantum computing really got rolling, really in the 90s. So when this algorithm, Shor's factoring algorithm, was developed. And basically, I'll tell you what Shor's algorithm does. Okay, and it sounds like a really very boring algorithm, but it turns out it is extremely important. So what Shor's algorithm is that if someone gives you a number, a large number, that is the product of two prime numbers, okay, and you know it's a product of two prime numbers, but you don't know what the factors are. Shor's algorithm is a is an algorithm that uses the laws of quantum mechanics and wave functions that I just described, and gets you the factors. You know, it takes a number that's a product of two factors and determines the factors efficiently. And what efficiently means is basically you look at the number of digits in the product, and it goes like a power law of the number of digits. Okay, so and then classically the best known algorithm is exponential in the number of digits. Right. And it turned out that totally revolutionized people's opinion of quantum computing. And again, it was an algorithm that you could, mathematically prove could factor in efficiently. So let me tell you why this mattered. Okay, so some of you are old enough to remember this. Okay, there was a time when I was even in college. Well, actually, even past college. So there were a couple things. There were no cash machines. Okay, there was no internet commerce, and if you went to use a credit card, what you would do is you would go to the store and you would give them your credit card, and they would call up the credit card company, and there was a person there, and then they would check on your number by calling them up on the phone. How many people remember that? Yeah, see, so it's not just me, okay? And we don't do that anymore, right? You swipe your card, you put it in, you understand, okay? And the reason why is because an algorithm was developed called the RSA algorithm, and R and S and A are Rivest, Edelman, and Shamir, okay, some guys. And what they did is they had a thing where basically you could encrypt basically the information using the product, this composite number that was of two large primes, and in order to decrypt, okay, you needed to know the factors. Okay, and what made this thing work, and the reason why all of internet commerce that we have today uses this algorithm, is that nobody knows how to efficiently factor large composite numbers. Okay, and so Shor's algorithm is a way of breaking all of internet commerce. Okay, and your cash machine and whatever. Okay, so you could see where people would be pretty interested in perhaps making one of these things. Okay, and in particular, the NSA has provided a large amount of funding because, again, so much of current day encryption is based on the difficulty of factoring large numbers by classical computers. Okay, now I will say that it's not proven by any stretch that you cannot factor large numbers on a classical computer, because in order to prove that that's hard, you have to solve the P versus NP problem, which is a very famous problem in computer science, which is unsolved. But again, people have been working on this for a long time, because if you could do this classically, you could basically break in all the banks and become a trillionaire overnight, and so clearly effort has gone in. But Shor's algorithm is definitely works. Okay, so based on that, even though it's not proven to be more powerful, it provided a real impetus for trying to build a quantum computer. Okay, so this one is the most interesting because it had an immediate, really practical application. If you like stealing money, really, really practical. Okay. And actually, like Edward Snowden had this, the NSA is funding work on quantum computing, and and we're like, well, yeah, duh, we knew this, right? But that's why the NSA funds this work, because of this. But that's not proven. But this is an algorithm that was developed very shortly thereafter, where it is actually proven that a quantum computer is faster than a classical computer, and so it's known, and but never mind. It's like once you've decided you wanted to build one, then that is the problem that actually that I've been working on mostly, and which is what I'm going to tell you about. It's like, let's assume we want to build one, and how do you do it? Okay. Basically, what happens is that you have this quantum system, and you're going to evolve it in a known way. It's just like in a classical computer where you say, oh, okay, you think about having, classical computers work with charges. Oh, we're going to take this thing, capacitor, and we're going to charge it up and then discharge it, whatever. Well, here what we're doing is we're going to have these quantum spins, and we're going to want to rotate this guy, and in a controlled kind of way. And so the trick of it, and what makes it hard, really hard to build one, is that you want to get in there and tell these spins, these qubits, what to do. Okay, so you have to be able to access them somehow, because you want to be able to control them. But on the other hand, there's everything else in the world, all the noise, and all the stuff, what we call the environment. And so you need to make it where you can get in there and tell it what to do, but have the environment not mess things up. Okay, and that's the overall problem. And so if you couple better, then you can basically manipulate it faster, but then the environment tends to also couple better. And so the trick is to be able to have you be able to couple in and have the environment not screw things up simultaneously, right? And the great progress over the last 10 years is that we've gotten much, much better at doing that than before then. Okay, so over the last 10 years, there's been tremendous progress. And again, the last part of my talk, I'll talk about the progress in silicon quantum computing, which is the kind of quantum computing that I do. But there are many different kinds, and there's a lot of really interesting work on different implementations. Okay, so basically, again, the idea is that you want to be able to get in there and make the qubits do what you want them to do, without having the environment measure the spins unintentionally. So that's the way I think about the environment. It's just getting in there and it's making a measurement, okay? And I told you before that when you measure a quantum system, it changes it, right? It quote, collapses the wave function. So you want to be able to manipulate it without collapsing it, all right? And that's the challenge, all right? And so what I'm going to show you are things where you have, just some measure of how well you're doing. So the coherence time is basically we're going to set this qubit going. We're going to make it move, all right? And it's going to be rotating around because it's just a spin, and we're going to make it rotate. And basically once it's measured, then it just points the same way afterwards, right? So it'll rotate until it's measured, and then it'll stop rotating. All right, and so that the length of time it'll keep rotating around before it gets measured is called the coherence time, and the gate operation time is just the time it takes to actually rotate around. Okay, and so that's what I want you to be thinking about, is that the actual manipulations are you're rotating the spin around, you're changing it from this direction to that direction, But then again, the environment is trying to measure it, and once it measures it, then you're done. Okay, so this is the figure of merit I'm going to talk about, and at this point, in order to do error correction, to do like an algorithm, like Shor's algorithm, the best that we can hope for is to have, you can do error correction, but you need really very good qubits, and that you need to have this figure of merit be about 1,000. So you have to be able to go around about 1,000 times before a measurement in order to be able to run a quantum algorithm, okay? And to do that, again, you need this ratio to be big, and so you need fast operations and long coherence times, and it's a very delicate thing, and so, the fact that, this has been achieved in several systems is, really, I think, an amazing thing, because, again, when even 2000, nobody had anything, and now several different implementations have qubits that do this, okay? So, and again, most of you had heard of quantum computing, and part of the reason is because there's industrial activity here. So here's Google. This one is Microsoft. There's also, there are a bunch of different, there's Microsoft, there's Google, Intel is in this business now, then there are some startups, there's IonQ, there's Rigetti, and so IBM is doing this, and again, it's because of the great progress in, that's been done making the qubits. So the leading, some of the leading technologies are these trapped ions. So there's a company called IonQ, which is the the main trapped ion company, and the IBM and Google are doing superconducting qubits. And again, these are the biggest. So the bunch of companies are doing 50, but at the moment, 9 qubits are demonstrated, but there's the bigger chips with more qubits have been announced, but I haven't seen any data on them. Okay, and then there's a group in Wisconsin actually working on neutral atoms that promises to have 121 qubits. But I also drew the picture here. You can sort of see what the equipment looks like. So it's not like you're going to have this right away. Okay. At the moment, it's we're still at that pushing the bleeding edge, and the amount of equipment is large and the expense is high, but things are progressing. Okay, so the current status is there's been tremendous progress. Okay, and so all of those things I showed you on the last slide have high fidelity gates. The single qubit gates are, have a figure merit of 1,000 or greater, okay? And, but on the other hand, they're not so big. Even what's coming down the pipe in the next few years are things of like 100 qubits. And our best guess for being able to run Shor's algorithm and break into all the banks is that we will probably need about you need a few thousand error-corrected qubits, but our best estimate of how many qubits that is in roughly 1 billion. Okay, so we have to get from that transistor radio basically to the iPhone in the quantum computing world, right? We have to get lots and lots of qubits in order to break into all the banks. Not that I want to break into all the banks, but I want yeah, I do, but okay. But the point is that if you really want to run Shor's algorithm on a number that's big enough that you can't do it, just running your classical computer for a week or two, you need a really pretty big quantum computer. So that's what motivates the work we're doing at Wisconsin on silicon. Okay, so the whole point in the beginning of the talk was, first of all, to motivate why people are, wanting to go down other axes to get more computational power. Because I have to say, like early in my career, it would be a thing where you'd do something and you'd be at the bleeding edge of, parallel computation and whatever. And if you just basically just waited a year or two, usually that was more efficient than like doing some special architecture of a computer. But again, we're hitting the end of the road there. And so, trying to say, well, look, that way of scaling isn't gonna, is going to be cut off. And so let's think about different axes. But on the other hand, if you want, in the end, you're gonna want a big quantum computer. And the one technology where we know how to make 1 billion transistors is the one that's in your pocket. Okay, and so, and this is why we were able to be funded at some level, because, the NSA really wants to break into everybody's communications, and they want to run, they want to break RSA, and so they want big quantum computers. And so even though our first qubit, which I will show you, because we of course we're in love with our first qubit, our first qubit wasn't until 2014, and the project started in 2000. And you may say, well, how was it that you were funded for all that time with 0 qubits? The answer is because at the end of the day, we, all that effort that went into scaling silicon could be applicable to our qubits. And so they sort of understood this, and they said, well, see if you can get it working. So that's what we did. And so that's what I'm going to tell you about in the last few minutes, is the work on silicon. And what I'm going to try to convince you of is that silicon is, that we're now at the point where we can say we see a path where it's going to be comparable to the leading technologies quite soon, and then we hope to be able to really scale it farther than the other technologies can be scaled. But again, we're not at that point yet. But I'm going to try to convince you that we've made really a lot of progress on that path, and it's plausible that they were right to have funded us for all those years. Okay, so let me tell you how it works. So this is our artist's rendition. It's a PowerPoint of how it works. So the actual material that we work in, the electrons do live in silicon, so I was not lying to you when I said the electrons are in silicon. But actually the material is the silicon's a very thin layer, and it's sandwiched in between an alloy of silicon and germanium. And the reason why that's a good idea is basically, I think the way to put it is that in most electronics, what happens is that the electrons are hanging out near the surface of silicon, and there's an oxide there, and the oxide tends to have a lot of roughness. It's not potential roughness. There are charges and loose and dangling bonds and whatever. So being right near an oxide interface makes it harder to control, where the silicon-silicon germanium interface is very smooth and nice, and is a sort of a nice surface for knowing exactly where your electrons are. Because that's the trick here, is that we want to be able to control our electrons very precisely. Okay, so this little orange thing, real silicon is not orange, you knew that. Okay, but this little orange layer is the silicon well, and the electrons hang out here. This is silicon germanium. But in principle, then, it just acts just like silicon. And there are current electronic devices. High-speed electronics tend to be this kind of device. So there are commercial electronic devices now that use these kind of structures. Okay, but then on top, basically, these are just metal gates, all right? And the idea is we're just going to apply voltages to gates and do all our operations by just, measuring voltages, voltages and currents. Okay, that's all there is to it, and which is how your phone works. That's how classical electronics works. This is the actual device that we took of some of the data I'll show you were taken on a device that looked just like this one. This is not the device. This is one that's just like the device, but same design. And you can see these are like little metal gates, and then we apply voltages to the metal gates, and everything is done just by applying voltages and measuring currents. Okay, that's all we do. Okay, and these things were basically what you do is you make these things negative, and electrons are negatively charged, and so they're repelled, and you do it just in such a way that there's like one electron here and one electron there, for instance. Okay, so you can actually control it. So there's like individual electrons in each one of these quantum dots, and you change the voltages, and you can move the electrons around, and you can do all the manipulations for the spins. Okay. And again, just to show you a picture of why we're pursuing this kind of architecture, is that basically this is our qubit with a few less gates labeled, but here it is. And this is actually a picture of a device from like actually 1988, and you can see, here are metal gates, and here are metal gates, and here's the superconductor, and it's the same technology. Things are a little smaller than in classical electronics, but not a lot smaller. Okay. All right. And so the experimental stuff I'm going to show you is done in the laboratory of a collaborator, Mark Erickson at Wisconsin. And we've been collaborating closely since I've been there, so it's for more than 15 years now. And then the theory, almost all of it was done in collaboration with Mark Friesen, and then these are various students and postdocs who've worked on this, in addition to a few outside collaborators. Okay, so I have a few minutes. I was told I have till 5 past, for those of you who are worried about the time. And I'm just going to show you a little bit about our recent results, just enough to try to convince you that we really, that we can make high quality qubits in silicon, and we are on the path to being able to make single qubit gates and 2 qubit gates. Okay, so this one is I'll show you a little bit of the single qubit gates and a little bit of, it turns out it's not like you just make it and it works. But over the last several years, we've understood much more about how you fight it's called decoherence, like how you keep the environment from measuring your qubit. And it turns out that we've learned a lot about that, and we've been able to improve things a whole lot so that our single qubits look quite good. And then just really recently, in collaboration with the group at Delft, we just published a 2-qubit device where not only can you do just one gate, but actually we can get it working well enough that we can run some simple quantum algorithms. And so that was just, it's at that point where it's published online, in a glamour journal, but it doesn't have a number yet because the print isn't out yet, but it's published online. Okay, so I'm just going to show you a little bit of data, just so you can see that we've made a lot of progress, and this is a really fast-moving field. So I just want to tell you a little bit about how you think about it. So again, what happens is you set your spin going, right? You do your manipulations, and they would go forever, except for the fact that the environment is screwing things up and is measuring this qubit as you go along. So what happens is that you see these oscillations, and they decay, okay? And the decay is this coherence time, and the frequency of the oscillation is essentially, tells you the gate time. So a lot of stuff I'm going to show you is done using grayscale. So again, the grayscale will sort of look like this. And again, if you sort of want to figure out what the figure of merit is, you just sort of count the number of stripes, and the number of stripes that you see is a very good estimate for the figure of merit. Okay, so what we're doing is we're going to count oscillations, and if the figure of merit's supposed to be, 1,000, then you need 1,000 stripes. You need 1,000 oscillations. So this is where Brand X is this is work by a group at HRL Laboratories in California, and this was the state of the art of silicon qubits in 2012. And we were able to do this, okay? And this again is from 3 years ago. And you can see that here, if we count 1, 2, 3, 4, 5, it's less than 20, okay? And here, if you count, you get 300 oscillations. So we were able to, really improve things a lot. Then it turns out, okay, I was telling you about the latitude and the longitude. The thing I was showing you is actually going around a constant latitude, but you still have to do the longitude. Okay, and it turned out that the one I showed you, Brand X from HRL, they do great work, but they're Brand X for me. They actually had like not even a full rotation. So in the thing I showed you before in 2015, we have like 5 oscillations. And again, 5 is not going to cut it, right? We need hundreds of oscillations. And basically over the last few years, we've just figured out how to do much, much better. And now for this, we have over 100. 100 is sort of marginally enough, but we have some theory work, which I'm not going to tell you about because experiments are so much more important. That we think we can get actually to several thousand. Okay, but we need a new device to do that. And so we're in the process of making devices that we think we can get 1,000 oscillations. And again, but this is based on in a couple of years, we really feel like we understand how to get really high fidelity, high figure merit in silicon. But I did want to mention the 2-qubit gate work. And again, this was this collaboration between us and a group at Technical University of Delft. And this is a picture of the device. Okay, so this again is the silicon in here. Okay, and here are the metal gates. This green and the blue is an artist's rendition of where the electrons are. Okay, so we know the device has 2 electrons in it. And it turned out to run the 2-qubit gate, it was sort of designed originally that this guy was supposed to be over there, but it turned out that the interactions weren't close enough, the electrons weren't close enough together. So by futzing around with those gate voltages, we ended up putting both on the same side. Okay, so here are the electrons. In this device, what happened is that there's a giant magnet. And that means that you can make a 2-qubit device with just 2 electrons. Okay, and I'm not going to get into any details, but I just want to show you a picture of it. But I did want to say, again, I showed you those things for the other technologies, and it looked really complicated. This one's equally complicated. Okay, so, and again, the reason why it's so complicated, so here's the device, all right? But then, first of all, you have to be applying voltages everywhere and high frequency voltages. It's all done at low temperatures. So again, not in your pocket. It's a low temperature situation. But then again, you want to not have the environment there. So you're applying these voltages, but you want to filter out as much of the environmental noise as possible. Okay, and that's the source of almost all of this complexity. Okay, is that combination of wanting to manipulate things really fast and really be able to push it pretty hard to get a fast gate, but without having the environment to disturb the qubits. And so there's a whole technology there, which hopefully we will be able to boil down, because again, if we have to do this for every qubit in a billion qubit device, obviously, that's not going to work. And that, by the way, it means that, scale up. I've told you, oh yes, it's silicon, we can scale it up. But obviously, I think we have a lot of work to be able to, cause that to actually happen. Okay, so this is actually my attempt to be a little honest to you. Okay, so this is actually the thing that just shows you that it's a real 2-qubit gate. Okay, so what we have again is the qubits are spins, okay, and so I've got 2 electrons, and I'm rotating 1 electron, and we're making the gate, it's rotating around, and the rotation frequency depends on the state of the other electron. So I make this guy go up and rotate it, and when I do that, I get this yellow curve, and then if qubit 1 is down, and I rotate the other guy, I get the blue curve, okay? And you can see the red curve is rotating more slowly than the blue curve. And that's all you need, okay? If you have a 2-qubit, if you can rotate the individual spins, if you can, do these operations on single qubits, and you can do what's called a conditional operation, that's all you need, okay? Everything else is just scaling up. Okay, and so that's why we're really excited about this work, and it works well enough that you can run algorithms. And again, if I had more time, I would explain these algorithms. But what you're supposed to notice that like this is like different, the probabilities of measuring different states. And here you see it's yellow. That's one of the states, and here it's blue. And the blue, and this is like it gets the right answer for the calculation. But it's late enough that I won't tell you how it works. But if you want, I can explain it to you, because these are like well-known quantum algorithms that people do as soon as they have 2 qubits. Anyway, so we're all excited about that because, again, it's like silicon is now on the map. On the map of, being able to scale up, okay, and make make qubits, and put them together and make a quantum computer. Okay, so I'm at the last slide, more or less, and again, what I hopefully convinced you of is, first of all, making a quantum computer is an interesting thing to try to do. Okay, it's technically very challenging, but it's interesting, and we've been making a lot of progress. And again, in silicon, just over the last several years, we've now gotten to the point where we can make high fidelity single qubits. And just in the last several months, there's this work that I showed you. There's also a group at Princeton and that have made 2 qubit gates. And we're this group at Delta, and this collaboration with Delta is the only one where we actually ran an algorithm. But there is a group at Princeton who's also making 2 qubit gates, and also a group at in Sydney that has made a 2 qubit gate. Okay, but it turns out the 2 qubit gates I showed you work, but they're not at that 99.9% level. So when I talk to you about the scale up of saying, oh, it needs to be, the figure of merit needs to be 1,000. So again, this is just sort of I don't want to say pathological honesty, but again, just so that you're not misled. It's not enough for the single qubit gates to have that very high coherence, but the 2 qubit gates also have to have that high coherence. And at the moment, they don't yet. Okay, so that's something we have to do. We think we have a path, but until you do it, you don't know that you have a path, but that needs to be done. And then again, we have to, if we do that, then we really have to focus on the scale-up problem. And again, the complexity of the circuit that I showed you is really the main thing. But once you know the physics works, it's, we're really optimistic that once we get the individual components working, then we can really focus on scaling, and then we know we can do that. So I just wanted to again thank all the collaborators, because everything I talked to you about was a huge effort. I mean, that was one of the reasons I wanted to show you the complexity of the experiment. These are technically extremely challenging, and I think it's just remarkable in all the areas of quantum computing. Right now, the experiments are truly heroic, and the progress has been astounding. But and again, I think in the end things will be simplified greatly. But when you're doing that at this point, they're really amazing experiments, and really, really interesting to see. And I want to thank all my collaborators. And we didn't get into all the things that Theory did. I could point out, we helped them with this and that. But again, I want to mention Mark Friesen in particular, but a bunch of people did really important work in getting all of this working. And so, and that's all I want to say, and I want to thank you.
I think there's time for some questions.
Yeah.
And Katie and I will be going around. You want to pick one out? Let's make sure. Mine's on.
Okay,
Is yours on? Okay, we could do a duet.
So please wait for the mic to ask the questions we want to hear.
Question? Let's let him go first.
Hi.
Okay.
Hi, thank you for your presentation today. I know stuff like this is difficult to estimate, but do you have a rough idea for when quantum computing will actually be able to replace the classical computing model of the binary system we have?
Okay, so you heard the question. It was like, what's the timescale for quantum computing? And this obviously people are. It's a matter of opinion. Okay. And so I'll just tell you my opinion. Okay, so there's there's a distinction that I want to make between error corrected and not error correction. So quantum error correction is possible, but when I talk about this, like, figure of merit of 1,000, or sort of the lingo is saying 99.9% fidelity in order to do error correction. The error correction is very challenging, and the current status of error correction is that people have, so I think that the IBM group and the Google group, I forget which one is which, but they've done error detection, but not correction. And then the other group has done correction of what are called bit errors, the analog of just being in the wrong thing, but not phase errors, okay? And now the Yale group has done something which is error correction, but in a non-scalable architecture. So I wanted to say that because basically the upshot is that nobody really has error correction no one really has error correction. Okay, and if you don't have it at all, it's really hard to know exactly when you're going to get it. So if you sort of talk to people, they're like, oh, error corrected, maybe 20, 30 years, okay? I'm hoping I'll be alive, but all right. So, and I'm not that old. I mean, I'm old, but I'm not that old. Okay. So but the reason why people are excited now is that if you don't worry about error correction, but just say we want to run our qubits, and we wanted to get the fidelity, this figure merit, which we're going to call the fidelity from now on. If you have the fidelity and it's like 99.9%, you can run an algorithm that's like 1,000 steps before the errors accumulate to the point where you're screwed. Okay, and basically, I think that's going to happen on the 5 to 10 year timescale. What we don't know is is there a really interesting thing that you can compute that way? Okay, so in terms of your phone. First of all of the technologies for quantum computing, the near low temperatures and the ion it's like no one's going to have them in their, in a portable way, even on a longer time scale than the 30-year time scale. But there will be some specialized applications, I'm pretty convinced, in the next 5 to 10 years where a non-error corrected quantum computer, but with good fidelity, can do something useful. Okay, but it's not going to be general purpose, it's going to be specialized. And I think for the general purpose, breaking into all the banks, we're talking sort of a 25 to 30 year time scale. You'll be alive. Yeah, but if you can break into one, why not all the banks? Why not get all the money, right? Anyway, so and again, there's a whole bunch about breaking into the banks. I won't go there, but there are more questions. And then if you want, I can talk about breaking into banks. Someone has a mic. Yeah, hi.
Hi, so my question is, suppose hypothetically you have a perfectly...
Show that the qubits can degrade if left itself.
Wait, there's a guy with a mic.
Sorry.
That's all right. But yeah, you get it next. Okay, yeah. Sorry, yeah.
Should I go ahead?
Yeah, go ahead. Sorry.
So hypothetically, if we have a perfect quantum computer that works as we want it to work, in that case, apart from robbing banks, what are some of the problems that would be within our computational grasp that we can't do right now?
Okay. Well, actually, this is where you're going to get a totally biased view because my background is in, condensed matter physics. And one of the things is that, but also I think the particle physicists to some degree will agree with this. So one of the things is that at some level you say, oh, we can't really do a very good job of simulating materials. And there is, and that's why, this is why I think the application is going to be, but for instance, if you do lattice gauge theory, and you want to understand, fundamentals of interactions between particles, it turns out that if you put fermions in, computationally, you get what's called the sign problem, and it's extremely difficult to get anywhere because basically the answer is a sum of a very big positive number and a very big negative number, and then they almost exactly cancel. And it is known that if you had a quantum computer, you can do efficient simulations of any quantum system. Okay, so from the point of view of physics, it's clear that if we had one of these things, it would be completely revolutionary because you could really simulate, in a very well-controlled way, essentially any quantum system with fermions. And right now, that's just not possible. Okay, so that's an application which I know I would love to see. And I think will be really important because all these things about strongly correlated systems. I mean, you would just be able to really just understand what's going on, and it's clear. And that would have implications again, for like what's in the inside of stars, and that kind of stuff is very clear cut that it would be totally transformative. In terms of other applications. To me, now I'm gonna get, okay, and that I would stand behind in terms of, knowing it's true. In terms of other applications, to me, the most interesting things about like doing things using quantum, using quantum stuff is this thing of, it's called quantum non-locality. And in my talk, it was sort of hidden, right? Where I said, oh, you have exponentially, you have n spins and you have exponentially many numbers. But it turns out that has an implication that, that there are certain problems that's called communication complexity of a problem, and that means that I have a giant computer here and a giant computer here, and they're trying to solve some joint problem, and they have to communicate. And how much communication do you need in order to solve the problem? And there are what's called huge separations. I mean, so if you had quantum computers and quantum communication, there are many problems where the amount of information you need to communicate goes way, way down. And that, to me, is actually going to be where the other applications that we haven't thought of but will be really important. This idea that you can, the non-locality of quantum mechanics reduces the communication cost, I think is going to be really important. Okay, but again, right now it's just like, and actually the Chinese have done a satellite and whatever, so you can do quantum communication, but people haven't found an application that people are willing to pay money for. But that's what I think is going to be a really big application at some point, because it's something qualitatively different about quantum communication and computation. Yeah, okay, and then, yeah, you have the mic? Okay, and then wait, he gets it after you, okay? Oh, you're there? Okay. Two mics are so confusing.
Okay, it's my turn?
Yeah.
Okay, thank you for this presentation, very good information. Actually, I have two questions.
Okay.
So my first question is, you mentioned it's hard to improve the fidelity of those quantum gate right now, right? So, but the corporate they are greedy, and we cannot, the corporate, like the company, they are greedy, and we can't wait until like 20 years to get like a universal quantum computer for us, right? So my question is, given the current technology and of the quantum gates, so what's the potential application you see which can be like commercially can be benefit for the corporations?
Yeah.
Okay. So my second question is, to scale up those quantum gate, you need a very high fidelities, right?
Yeah.
And you mentioned it's very hard to achieve those goals. So what do you see the chance to across that threshold for the quantum dot technology?
Yeah.
Or comparing to the I know some company are looking into the topological quantum technology, right?
Yeah.
So compared to that technology, what's the advantage of the quantum dots?
Oh, okay.
Okay.
Let me do, well, I'll do the first. I think I can remember them both. Okay, so the first one is sort of like, what are the near-term applications? And I think, again, these applications to understanding properties of materials are going to be fairly near-term. I think that basically you can think about that where a quantum simulator can really lead to yield new qualitative insight. And I think that, just looking at the successive density functional theory, and it's been very, there have been, done predictions and been very useful. That will, I think, be the near-term application on the 5 to 10 year timescale. And I hope so, because again, that to me is sort of the most plausible thing, because error correction is a big challenge. Okay, so then the other thing you pointed out was like the quantum dots versus the topological quantum computation. And the topological quantum computation, this is the approach that's being the main focus for it is at Microsoft. So this is the approach that they've been following, and it's an amazing thing in the sense that if it works, then the qubits sort of at the microscopic level should have much higher fidelities. Okay, and that would just greatly reduce the cost of error correction because you start off. If you think about, again, how many steps can you take before you lose coherence? If they're like, 10 to the fifth better, that you can take 10 to the fifth more steps, okay? And it's, to me, an incredibly exciting and interesting thing to do. At the moment, they have 0 qubits. And so it's just a wonderful thing. It could be fantastic, but until they have more than 0, you don't know. Okay, and there are things that could go wrong. I mean, it's not something that is guaranteed to work. And so to me, it's like a wonderful way for someone to be spending money because it's the physics is really super interesting, and if it works, there's a really high payoff. Okay, so the theme of the quantum dots is sort of what we've learned is, basically the way it works is that you have a thing, and you start off and the fidelity is sort of okay but not great, but then you figure out what's your main source of decoherence. And it's like haiku in some ways. It's sort of a very constrained problem, right? And this is the thing with the funding, right? You're trying to get a quantum computer to work, so you say, oh, it didn't work, but we discovered this other thing. Like they're not interested, okay? But so in that sense, it's like haikus, okay? But what we found is that you figure out what the main source of decoherence is, and usually, like if you understand it, then you can figure out like how to change the design, or you figure out a way around it, okay? And then that's no longer your dominant decoherence mechanism, then you got to figure out what your problem is next, okay? And then you beat on that. And so it's just an iterative process. And that, to me, is the most amazing thing, is that, the superconducting people have done this, like, for generations, and they've gotten, factors of 100,000 in the coherence. And they just, you just keep beating them down, and it's just these things, once you know what you're doing, you just, people have been able to just iteratively improve them. And so right now, the single gates for superconducting qubits are, have amazing fidelities, like 10 to the fifth figure merit. And so we're behind, just because our first qubits were, the first superconducting qubits were in like 1999, and the first, semiconducting qubits were much later. And so we're going up that curve. And I think, again, you keep beating on it, and it keeps improving. It's amazing. And, the ion traps are the same way, where, again, the people have fidelity versus time, and it looks like Moore's law. So that is the thing where if the topological qubits work, they'll go on their own Moore's law, and they'll keep getting better. But I don't believe that there's like any one technology which is obviously better than all the rest. Okay, and I think again at this thing of like saying, well, maybe we can, once you know how to make really control quantum systems really accurately, they'll be good for something, and the different platforms will be good for different things. So I tend to be quite optimistic overall. I mean, I don't think, oh, well, this thing works, and so therefore everything else is useless. I think they'll be good for different things. Okay. Yeah, okay.
So I hope this isn't a sidetrack, but I hope you've thought about this. When somebody develops that specialized quantum computer and they break the banks, that means you really don't want to do that, because if you have all the money, then money isn't worth anything anymore.
Oh, if you have all the money, yeah.
My point is, or my question is, have you thought about, is there an alternative encryption algorithm that will be available before somebody's?
Okay, so this is actually a really interesting question. And I'm on actually a committee where we're actually studying this question. And the short answer is that there are other encryption algorithms that can be used instead of the things that are susceptible to quantum attack. Okay, but they're all much, much worse for the users. So people don't want to change to these other ones because there's like a key, and the key size is much bigger in order for the same number thing, and they're easier to spoof because I don't know if you know anything about cryptography, but there's some numbers you have to use for your key, and that's how you generate your code. And if you use the wrong key, then it's easy to break. And the NSA was sending out bad keys so that they could break into everybody's stuff. This was again another Snowden thing. And that's all even worse for these quantum-resistant algorithms. And so there's tremendous resistance to doing this. And so that's why they wanted to say, well, do we know that we have to do this? Because the time scale to switch the cryptographic system is roughly 20 years. So the question is not, is there going to be a quantum computer that can that can run Shor's algorithm now? The question is it going to be here 20 years from now? And that's a different question with huge uncertainties. And again, the price for being wrong is very large. And so I thought about it, and but the good news for me is, again, I'll probably be dead. So whatever happens, I won't have to see. But that's not really the good news, is it? You could say the same thing about global warming, right, for us old people, but that's not really a good answer, is it? But people are studying that problem. But that's the problem. There at the moment, all of the quantum resistant, the algorithms that are resistant to quantum attack are much worse for the users, and so people don't want to change if they can avoid it. And then there's one more.
There's one last question.
Yeah.
You may have hit on this one already. I'm not 100% sure. Does the qubit share the characteristic of a DRAM that it has to be continually recycled or refreshed, or the data in that bit is likely to disappear?
That's a great question. So it was this question of, does it need to be refreshed?
The mic wasn't working, so will you repeat the question?
So the question is what about, this is quantum memory versus DRAM, or do you need power and keep cycling it? Okay, that's the question. Do you have to keep doing error correction on it? And this is a really interesting question because of there are systems where the memory is really, really long. Okay, and you can sort of see, if you're just saving the information, then you can just isolate it from everything. The thing is that if you're doing the computation, you have to be in there manipulating, right? And so that's one of the things of can you sort of come up with a design of something where when you're manipulating it, you're coupled to it, but then you can make it so it's totally impervious to everything, and then turn on the coupling. Okay. And some of this is done using hybrid systems. So in terms of memory, people really like photons, because photons couple with light, because it couples very weakly to matter, and you can just put it in a mirror and it'll go around, and it can last a really long time. But the short answer to your question is that in principle, you could imagine making a quantum memory that didn't need a very often refresh, but then you have to figure out how you're going to get the stuff in and out. And it's not clear whether we want to do that or not. But people are working on that, trying to decide whether a separate memory that doesn't need to be refreshed is worth it. But again, we're futzing around with 10, 20 qubits. So, we're not up to the point where we actually have an opinion on it. And no one has more than 20 qubits at work at the moment. Okay, but it's a great question, and people were working on it, but we don't know the answer yet. But in principle, yes, you could have a memory that doesn't need a refresh. In silicon, the time can go up to several seconds, just bare, with nothing fancy. You can get a several second coherence time. But again, you can't access it. You put in the nuclei don't couple to anything. It's actually amazing how coherent it is. I hope that answered it, but. We don't know. The short answer is we don't know yet.
That's thank you.
Okay.